All right, so we want to talk about error detection. And basically when talking about error detection, the topic just talks about the part that we have two guys who just want to communicate, right? We have A and B who want to share information, right? So as A wants to send information to B, A is going to be sending some data, but B needs some form of mechanism now, or the two guys need some form of mechanism that they're going to be using now to validate or to verify if the information that has been received by B is the same information as was sent by A. Are we together? So for that reason now, the different mechanisms that can be used to verify to validate the information that has been sent to B are the ones that we're going to be calling error detection mechanisms. Are we together? So there are quite a number of mechanisms that we can use, but to start with, we'll talk about the parity check. So parity check happens to be one of the methods that we can use so as to verify whether the information has been sent correctly or not. Parity check now, the first point that we're going to be raising is that it takes advantage that when information is being transmitted, it's transmitted as a stream of bits, right? When information is being sent from A to B, it's going to be sent as a stream of ones and zeros. So we're going to be having 1, 0, 1, 1, 0, 0 is the information that's going to be sent from A to B. Altogether. That's the first point that you need to be appreciating. The second point is that when information is being transmitted from A to B, it's sent in streams of bits and in form of blocks of bytes. Are you getting the point? Blocks of bytes. So when talking about blocks of bytes, a byte consists of how many bits? 8 bits. So we're saying that each block is going to be containing a byte, which is going to be consisting of 8 bits. So we are saying now, for instance, we're sending information like 1, 0, 0, 1, 1, 0, 0. That's 2, 4, 6, 7, 8, like this. So when a byte like this is being transmitted, parity check now will make sure that 7 of the bits are reserved to the data that is being transmitted, the data itself. Then the last bit now, it can actually be the first bit, or let's just say the 8th bit, either the first one or the last one. We do not care where the position of the 8th bit is concerned. But the 8th bit is going to be reserved as the parity bit, the one that is going to be used by the system itself. Is reserved as the parity bit. Is that making sense? So this bit now is auto-populated by the system itself. It's not you populate this, is auto-populated by the system based on the type of parity check that is going to be used. So the system can actually be used odd parity, or it can actually be using even parity. So parity check can actually be in the form of odd parity or even parity. When it's using odd parity, it's saying that the number of bits, right? When it's using odd parity, it's saying that the number of ones, the number of 1 bit, so let me just put the number there, number of 1 bit in the byte itself is supposed to be odd. It's supposed to be odd. When we're talking about odd numbers, we're talking about numbers that are not exactly divisible by 2. We're talking about 1, 3, 5, and 7. So the count of the number of ones in the byte are supposed to be odd if the system is using odd parity. Do you get the point? When we talk about the part of even now, even is saying that the number of ones in the byte itself, the number of 1 bits are supposed to be what? The number of 1 bit is supposed to be even. When we talk about even, we're talking about numbers like what? 0, 2, 4, 6, or even 8. The numbers that are exactly divisible by 2. Are we together? So take this example now. Suppose that the information that is being transmitted from A to B, right? Suppose the information that is being transmitted from A to B consists of 1, 0, 0, 0, 1, 1, 0. So we have 1, 2, 3, 4, 5, 6, 7. This is the data itself. So what's left now is the parity bit. Are we together? So suppose the system is using odd parity. what is going to be in this, what is going to be the value of my parity bit? Suppose that the system is using even odd parity, and the data that is being transmitted consists of 1 0 0 0 1 1 0. What is going to be the value of my parity bit? The value of my parity bit is going to be 0, such that at the end of the day, if I then count the number of ones that are in this byte now are supposed to be odd. I already have 1, 2, 3. I already have 3 ones that are in here, right? So 3 ones are already odd. So the parity bit is either a 1 or a 0. Always is either a 1 or a 0. So the auto population will result in us having the value of the parity bit as 0. Why? Because we already have the number of ones as odd. But if this system was using even parity, then this was going to be a 1 to make sure that the number of ones are now even, because I already have 3. If I add another 1, then I'll be having 4 ones, of which 4 is an odd number. Is it making sense? Is it making sense? So let's take another example again, that I have 1 1 1 0 1 1 1 is the data. What is going to be the value of my parity bit if the system is using even parity? She's saying that it's going to be 1, but that's wrong. Why? Because even, it's making sure that the number of ones in the whole byte are supposed to be even. In this sense, I already have 1, 2, 3, 4, 5, 6. I already have 6 ones. 6 ones, they're already even. So what I'm supposed to be adding here is 0. Why? Because the number of ones are already even. I hope that makes sense now. Yeah. So what's going to be happening now is this. When A has sent now this whole block now to B, what B is going to be doing is one thing, just to count the number of ones that are in the byte that has just been received. So all what B is doing is to count how many number of ones are in here. If these two guys have agreed that we're going to be using even parity, if B receives this information, B will say that this information is correct. Why? Because we have even number of ones. But if these guys have agreed on even parity, then B receives this information, B will say that this information is wrong. Why? Because the number of ones that are there, they are not even. So basically we are saying that when we talk about even parity, the number of ones in a byte are supposed to be even. When we talk about odd parity, the number of ones in a byte are supposed to be odd. If otherwise, then the data has been transmitted in error. That's basically what's up as far as parity check is concerned. Does that make sense? So you see now, what B is only doing is the part on keeping track. This is now the downfall now of parity check. Let me just put that in red real quick. This is why people hate now parity check in a way, if there is anybody who hates parity check, that is. We are saying that what B is all doing is the part on checking if they are odd, if they are even number of ones in the byte. Once they are even, then the assumption is that the data has been transmitted correctly. But imagine now, what if this 0 decided to switch positions with this 1, such that the data was received now is 1 1 1 1 0 1 1 0. In this scenario, if B is going to be counting the number of ones here, B is still going to be seeing the number of ones as 6. You see that? But the arrangement of the number of the ones now has changed here. There is some transposition that happened whereby this 0 exchanged positions with this 1. And B is not able to identify that. Once there is this transposition, the whole meaning is already changed already. But B is not able to see that part. So in that scenario now, we are saying that there is an error of transposition. So, come on. This is me failing to write the spelling of transposition. Transposition like this. That's exactly what just happened there. B is not able to identify if there are any bits which just exchanged positions, or B is not able to identify if there is any error of transposition when data was transmitted. That's where we have the faulty part as far as parity check is concerned. Do you get that?
Yes, sir.
So, One downfall of parity check, it cannot identify errors that have to do with bits having transpositioned. That's what's up. Any question? All right. That marks the first part as far as our parity check is concerned. The whereabout or the way to avoid this type of an error happening is making use of what is called a parity block. So I will leave this up to you now to go and research on what a parity block really is and how it's used to avoid or to identify the error of transposition when data is being transmitted. Right? All right. Other than that, let's move on to talk about the second type of check, the second type of error detection that can be used. And A and B again can make use of what is called checksum. We talk about checksum. It's an error detection that encompasses the use of what is called a checksum value. A checksum value. So basically what you're going to be having as far as this is concerned is this. A will write a message that will be plain, right? A plain text that is readable to everybody. Let's just say that comms is fun. That's the message that comms is fun. That's what A wants to send to B, basically, right? A will first take this data into a hashing algorithm. Into a hashing algorithm or an algorithm, a hashing system in a way, which will produce now a checksum value. So the plain text is taken through a hashing algorithm to produce a checksum value. A checksum value basically is a hexadecimal value that is unique to every text. Do you get the point? In most cases, it's going to be coming through in hexadecimal. So let's say that when I take this plain text into a hashing algorithm, what is produced is actually called a checksum value, or some books they will call it a digest, right? So let's take for instance that what is produced is 3, 4, A, D, 0, 1, F. This is the value that has been produced by this text, right? So the first thing is A will write a plain text, and the system will take the plain text into a hashing algorithm to produce a checksum value. So what is going to be sent to B now is the composition of the two things. One, plain text, and the checksum value. Are we together? So data is going to be sent together with the checksum value to B. Are we together? So B now will receive two pieces of information. So B will receive two pieces of information. One, the plain text and the checksum value. So if B now wants to verify if the information has been sent in error or not, B will take the plain text and also take the plain text into the same hashing algorithm that was used by the sender. So basically, B will recalculate the checksum value. Do you get it? B will recalculate the checksum value to produce his own checksum value. So this is the checksum value, B's checksum value. B will then take this checksum value and compare now with the checksum value that has been received from A. Like this. Checksum value from A. So this checksum value from A. So we are saying B will produce his own checksum value and compare it now with the checksum value that has been sent from A. If these two checksum values match, then this data was transmitted correctly. Because if somebody tampers around with this information, let's say probably and just adds a full stop, then the checksum value is going to be different. The checksum value is unique to every text. So we are saying that the plain text received now by B, B will receive the plain text and the checksum value, and will do a recalculation of the checksum value. So the checksum value recalculated is then compared with the original checksum value that came together with the data. If these two guys are the same, then the data or the transmission was successfully done with no error, with the data you haven't been tampered around with. That's basically how checksum works. So basically it works like this. In summary, A writes the plain text. The plain text is placed in a hashing algorithm. Hashing algorithm produces a checksum value. The data is then sent. The plain text is then sent with the checksum value. B receives the information with the plain text and the checksum value. B will first take the plain text and place it in the same hashing algorithm that was used by A, right, to produce his own checksum value. The two checksum values are then compared. If they are the same, then the data has been transmitted correctly. If they are not the same, then there is an error that just happened. Are we together? That's as far as checksum is concerned. Let me just close this up and talk about the part on automatic repeat request, ARQ in short. Automatic repeat request. We could have just said ARR, so but we just chose to call it ARQ. So it's automatic repeat request like this. We're going to be putting it like this so that you see exactly why we chose to write the queue. Basically. So for this now, let's just go green with it. When we talk about ARQ now, we are talking about this. A wants to send information to B. Right? What's going to be happening is this. A will send, okay, let's have it like this. A will continue sending the same message to B until B acknowledges that he has received the information. If B did not, if B doesn't respond or doesn't acknowledge that they've responded, they've received the information, A will keep on sending the information. That's why it's called automatic. Automatic repeat. So the sending of the information is going to be repeated until B acknowledges that they've received the message. Are you getting it? So we're saying it uses acknowledgements and timeouts to make sure that the user receives the data. You get the point? It uses acknowledgements and timeouts. So talking about the part of acknowledgements, you can just write the correct spelling, and timeouts. So having it like this, A will send information to B. Let's say the timeout is let's say it's 1 minute, right? So A will wait for a minute to receive feedback from B. So the acknowledgement may be a positive or a negative one. Positive or a negative one. A negative acknowledgement will indicate that B will be just saying to A that I have received the information but it's not complete. But a positive acknowledgement is just B responding to A again that the information that I have received is complete. Do you get the point? So A will wait for a certain period of time before he does the resend. Do you get the point? That's what we're calling a timeout. So we are saying now, A will send information to B. B has an obligation to send a positive feedback if he has received the entire information. B has an obligation again to send a negative acknowledgement if the information that he has received is not enough. Do you get the point? If B is remaining quiet, then A will wait for a certain period of time. For this example, we're going to be talking about a minute, to resend the information again to B. Do you get the point? So we are saying now, taking that one more time, we are saying that uses acknowledgements and timeouts to make sure that the user receives the data. Check this part. The receiver would check the data for any errors, and if none are found, a positive acknowledgement is sent. So we only send a positive acknowledgement if there is no error. If there is no error in the data that is received. You get the point? Then we will send now, however, if any errors are found, a negative acknowledgement would be sent. So a negative acknowledgement is sent if there is an error in the data that is received. Are we together? Are we together? Check this last part now. Timeouts are used by the sender. So the timeouts are specifically for the sender. You get the point? What are they going to be doing? We're saying that they're used by the sender to wait a predetermined amount of time for the acknowledgement. So A will be saying that I need my response in the next 1 minute. If I don't get the response in the next 1 minute, I'm going to be flooding you again with the same information that I sent you the first time. You get the point? Just like your parent is going to be calling you. The parent isn't going to be stopping to call you until you respond. So if I'm going to be calling you Denzel, I will only stop calling you Denzel until I get a response you saying that, hey, yo, I heard you. Do you get what I'm saying? So if I don't hear you responding to me, I will assume that you haven't heard me. So I will keep on calling you until you respond. You get the point? So basically we're saying that if no acknowledgements are received after the timeout, the data would be sent again to the receiver. I hope that makes sense. That's basically as far as AR kill is concerned. It uses acknowledgements. So if I'm asked to summarize the probably AR kill, I'll be saying this. AR kill uses positive and negative acknowledgements and timeouts, right? The sender sends information to the receiver and waits for a predefined time or for a preset time to get a positive or a negative feedback. Altogether, a positive acknowledgement will indicate that there is no error in the data, but a negative acknowledgement will indicate that there's an error that is in the data. Altogether, if the timeout set time lapses without any response to A would then automatically send the same message again to B with the assumption that B has not received the information. Are we together? Are we together? Any questions? All right, if there are any questions, you can just chew on these, and we'll talk about the check digit later on. But for the meantime, you can just chew on these three that we just discussed. If you have any question, you can still touch base.